Hall, from which has developed the reactors of the first stage of Britain's nuclear power program, was opened by Her Majesty the Queen in October 1956.
It is with pride that I now open Calder Hall, Britain's first atomic power station.
18 months before this, such was the confidence in the basic design that the government had formulated and published a program of nuclear power. At that time, Calder Hall was only half built, and since then the program has been modified to meet changed conditions. At present, the plan is to have an installed capacity of about 5,000 megawatts in operation by the end of 1968. Contracts for the first 3 stations were awarded early in 1957. Their combined electrical output will be about 900 megawatts. Within a year, a 4th station was started with an output of 500 megawatts. In June 1959, a 5th contract was placed, again for a 500 megawatt station. Since then, construction has started on 2 more stations with progressively higher outputs. Of these 7 stations, 6 are on the coast or on a wide estuary. The 7th is beside a lake. By 1962, construction will have started on an 8th station at Oldbury. These commercial stations, designed and built by groups of industrial firms under contracts from the electricity authorities, are major engineering constructions involving the use of many new techniques. Goliath cranes were used on several stations for the heavy lifts, such as this lower section of the pressure vessel for one of the Hinkley Point reactors. For the heat exchangers of the Bradwell station, an ingenious solution was found to the problem of transport. After assembly at the maker's works, they were launched into the sea and towed down the coast to the site. Bradwell is another station where a Goliath crane was used for heavy lifts. Not only on sites is the work being carried forward, but in many industrial centers throughout the country, manufacture and research are assisting the program. The fuel elements for these stations will be supplied from the Springfields works of the Atomic Energy Authority. Here, a large new plant has recently been completed, incorporating the experience of over 10 years in the manufacture of fuel for gas-cooled reactors. The design of fuel elements varies from station to station, and to cater for this, separate canning lines are installed for each type. For some time, deliveries have been taking place to the early stations. And both at Bradwell and Berkeley, the first reactors have been loaded and are expected to be on power early in 1962. As this was the first charge of fuel elements, they could be loaded into the reactor by hand, with a considerable saving of time. The amount of fuel needed for criticality agreed closely with theoretical predictions. While these early stations are ready for the commercial generation of electricity, other stations are in various stages of construction. Meanwhile, Calder Hall has been working for over 5 years, providing valuable information on both the behavior of fuel and station operation. This experience is being used to improve the fuel elements for the new power stations. Less than a mile away is the advanced gas-cooled reactor, prototype of the next stage in the development of graphite-moderated gas-cooled reactors. The site work started in 1958 with the excavation for the foundations 35 feet below ground level. It's planned to operate the reactor at a temperature 150 degrees centigrade higher than the Magnox stations. And although the principal change needed to permit this is in the fuel element, it materially affected the overall design. Because of the compact design of the reactor and its 4 heat exchangers, it was possible to enclose them in a steel containment building. And construction of the lower part of this began simultaneously with the placing of the concrete for the reactor biological shield. The heat exchangers also were to be provided with concrete shields supported on steel brackets built into the reactor shield wall. The reactor vessel is linked to each heat exchanger by a single straight duct, and all the vessels are supported at duct level. This eliminated the need to compensate for thermal expansion vertically. Horizontal expansion is accommodated by mounting the heat exchangers on ball-bearing supports, which allow lateral movement. The design of the heat exchangers provided for them to be built in 3 sections, each of which could be tubed at the manufacturer's works before dispatch to the site. In the base of the bottom section is installed the diffuser, which will be linked by a right-angled bend to an inner duct carrying the hot gas from the reactor. The tubes are enclosed in an insulated box so that the hot gas flows up over the tubes and, when cool, returns down the sides of the vessel, thus minimizing the temperature to which the pressure shell is exposed. Another novel feature of the design was to set the circulator in the base of the heat exchanger, from which the cool gas is returned to the reactor through the annulus of the duct. A steel diagrid supports the graphite core. Its design was dictated by the triangular lattice adopted for the fuel channels. Graphite laying followed the normal procedure. The blocks were fed into the reactor through one of the heat exchangers and its connecting duct. The principle of sweeping the inside of the pressure vessels with cool gas was applied also to the reactor, and the core is surrounded by a thermal shield. The slots formed by the graphite bricks provide paths for a fraction of the cool gas, and so reduce the moderator temperature. Above the graphite core was built a neutron shield to reduce activity in the upper part of the reactor. The hot gas flowing up the channels through the core and neutron shield is collected in a manifold, the hot box, which is linked to the 4 inner ducts carrying the gas to the heat exchangers. When the neutron shield was complete, this hot box, which had been suspended in the top dome, was lowered into place for the charge tubes to be fitted, a separate one for each channel. On the charge floor above, the 400-ton refueling machine was being assembled. The fuel elements to be used in AGR consist of stainless steel or beryllium cans filled with pellets of uranium oxide. The use of this ceramic oxide in place of metallic uranium as the fuel and a more refractory canning material permits the operating temperature to be raised by more than 200 degrees centigrade. The individual elements are assembled in clusters and are located inside graphite sleeves. Three of these sleeves are linked together to form a complete fuel stringer for one channel. The design of the advanced gas-cooled reactor is intended to ease siting problems, and its startup in 1962 will mark a notable advance in the graphite-moderated gas-cooled system. Although for the MADMOC stations, output per reactor has risen from 36 megawatts at Calder to 290 at Sizewell, gas outlet temperatures are limited and have shown little improvement. In this respect, the AGR will be a big step forward. Again, the mean fuel rating at Sizewell is less than double that of Calder, but AGR will show a further threefold increase. Research into gas-cooled reactors operating at even higher temperatures is at present concentrated on the Dragon project at Winfrith. This international undertaking, to which Euratom and 6 other countries are contributing, consists of a 20-megawatt reactor, which is due to go critical in 1963. A fuel temperature of 1200 to 1500 degrees centigrade is anticipated. Already, information on the reactor physics of the system has been obtained from Zenith, a zero-energy reactor, in which the temperature conditions of Dragon are simulated by circulating hot nitrogen. Meanwhile, at Dounreay in the north of Scotland, an entirely different reactor system is being developed. This is a fast breeder reactor which can use plutonium as fuel. The reactor itself consists of a stainless steel vessel in which is enclosed the core of enriched uranium, surrounded by a blanket of natural uranium. Connected to the vessel are the primary heat exchangers. To provide biological shielding, the reactor and primary circuit had to be enclosed in a reinforced concrete vault, on top of which was installed a rotating crane to handle equipment. An airtight steel sphere is intended to prevent the dispersal of radioactive materials in the unlikely event of a sodium coolant fire. An airlock provides access. The skirts and center anchor bore the whole weight of the vault and sphere and transmitted some 10,000 tons through to the foundations. With the foundations complete, the center anchor was installed. and erection of the sphere started. The construction plan was to build the lower half of the sphere, then to construct the biological shield inside it, and after that to complete the sphere except for the last plate, which was left off to provide access for the delivery of components. The airlock panel was installed just below equator level. Meanwhile, development work, which had started long before, was proceeding in laboratories in many places. The fuel elements consist of hollow rods of enriched uranium enclosed in niobium cans. The close spacing of the elements is possible because no moderator is used in this fast fission reactor. With the completion of the vault shielding, the work on the top half of the sphere could proceed. The size of the vault was dictated by the need to enclose the whole of the circuit through which the primary sodium coolant flows. Liquid sodium had to be used to achieve the necessary high rate of heat removal, but it has the disadvantage of becoming radioactive, thus necessitating complete shielding. The first items to be installed in the vault were the electromagnetic pumps used to circulate the liquid metal coolant. These pumps have the advantage of having no moving parts and requiring no penetration of the circuit. The primary heat exchanger system consisted of 24 units in parallel. This was on account of the limited capacity of the pumps, but it also provided valuable protection against loss of coolant flow. These units each contain a central tube carrying the primary coolant, which gives up its heat to the secondary coolant flowing around it. This is also a liquid metal, but does not become radioactive. In the secondary system, the heat is transferred from the liquid sodium to water to raise steam. To avoid the possibility of a leak from one to the other, each unit consists of 5 separate tubes bonded together by copper laminations. The inner tube containing water and the 4 outer tubes, sodium. While the heat exchangers were being manufactured, the reactor vessel had been fabricated and was delivered to the site for installation. The stubs on the outside of the vessel will link it to the primary heat exchanger units. The elaborate system of pipework around the vessel and the constricted conditions of working were not allowed to lower the standard of workmanship attained by the fitters and welders. Inside the vessel and surrounding the core are the breeder element support plates. The reactor vessel was surrounded by a graphite shield to protect the secondary coolant system from neutrons escaping from the core. The top of the reactor vessel is sealed by 2 rotating shields, which, by independent movement, can locate any desired channel in the core or the blanket. In operation, the top shielding is completed by a plug. The fast reactor experiment first went critical in 1959. and has already provided a great deal of information from which it's clear that a commercial fast reactor will show major differences in design. By the late 1960s, the thermal reactors of the current stations will begin to provide an increasing stockpile of plutonium as a byproduct, and it's hoped to burn this plutonium efficiently in civil fast reactors, starting perhaps in 10 to 15 years' time. Dounreay, therefore, in a real sense, represents the key to future economic supplies of energy and stands as an important landmark in Britain's nuclear power program.